Today we're going to talk about analyzing the graph of a polynomial function. So first we're going to determine the end behavior of the graph for the function. Then we'll determine the x and y intercepts of the graph. And then we're going to determine the zeros of the function and their multiplicities. We're going to use this information to determine whether the graph crosses or bounces the x-intercept at each x-intercept. And then if we need to, we'll use a graphing utility to help us graph a function. So let's just go ahead and start looking at this first equation that we have right here. The first thing I'm going to do is try to factor our equation if possible. So we know we have a greatest common factor here of x, so I can take out the x, and then that becomes, and let's take out negative x, so this becomes x squared plus 5. And then we can set each factor equal to 0 to solve for the zeros of the functions or the x-intercept. So negative x equals 0 and x squared plus 5 equals 0. So here we get x is equal to 0 and x squared equals negative 5. Take the square root of both sides and you plus or minus your answer. You get x equals plus or minus the square root of negative 5, which gives us x equals plus or minus I root 5. So that means we have two imaginary solutions and just the one real solution for this. And so remember, we don't graph our imaginary solutions. So for this one, we have our one real solution at x equals 0, which would be right here at 0, 0. I'm just going to label this. And so for this one, if you have an x-intercept at 0, that means your y-intercept has to also be 0. But if you're unsure, you could always plug 0 into your equation to solve. So you get negative 0 cubed minus 5 times 0, which gives us 0, which shows we have 0, 0 as our point. So we have our x-intercepts, our y-intercepts, and then for this, we know that this is a polynomial of degree 3, which is odd. And the leading coefficient is negative. So odd negative means that the right end goes up and the left end is going to go down from the 0 that we have. And we only have this one 0. So our graph just kind of is going to go up like this and down like something like this from the 0. And so we actually don't need a graphing utility for this one because, again, we don't really have any max or min to worry about because of the fact that we just have that 1, 0. So looking at number 2, let's go ahead and do the same thing. First, let's take out our, well, this is 4 terms, so we're going to do factor by grouping. So we'll take out our GCF from each of our different groups. So in this first group, we can take out x squared. And in the second group, we can take out the 5. And remember, when you're doing factor by grouping, these factors have to be the same. So this gives us x squared plus 5 times x plus 2, and then now we can set each factor equal to 0 to solve to find the zeros of our graph. So again, notice we have 0 equals x squared plus 5. So we just did that a minute ago, right? So we know this is going to be x equals plus or minus I root 5. And then here we get x equals negative 2. So on our graph, we have negative 2 for an x-intercept. And then let's go ahead and find our y-intercept. So if I do f of 0 and plug that in for my x's, I would get 0 cubed plus 2 times 0 squared plus 5 times 0 plus 10. So you can see that your y-intercept is at 10. Let's count maybe by 2. So 2, 4, 6, 8, 10. So we have 10 right there. And then this is a polynomial of degree 3, and the other two zeros are imaginary. So this is odd, and the leading coefficient is positive. So that means the left end is going to go down, and the right end is going to go up. So from our graph, from our 0, we just have to go up through our y-intercept here, and then this would just go down. And again, for this, we know that you don't want to make it a straight line because it's not a linear function. but this would give us all of our important features for our graph. So let's say we did have some other zeros, and so we're going to approximate the turning points of the graph. We're going to use the information in steps 1 to 5 to draw a complete graph of function by hand, which we already did, and then we're going to find the domain and range of the function and use the graph to determine where the function is increasing and where it's decreasing. So looking at this first graph, now that we have it all graphed out, our domain of this, of course, we know there's no red flag, so it's all real numbers. And the range is also all real numbers. So then looking at the next part, we want to write down our intercepts, which we know we said our intercepts were just at x equals 0, so 0, 0, and 0, 0 for the y-intercepts. Oops. And then we're increasing none. So notice as we look from left to right on our graph, our y values are going down the entire way. So increasing is none, and decreasing would be from the interval negative infinity to infinity. So the end behavior, we're going to use our limit notation, would be the limit as x approaches negative infinity for the function is going to be going up towards positive infinity, and the limit as x approaches positive infinity for the function is going down towards negative infinity. So that would be our limit notation. So for the next one, our domain, again, there's no red flag, so all real numbers because there's no variables underneath an even root or in the denominator because we're working with polynomials here. The range in this case is all real numbers as well. The intercepts we said were x equals 2, so we have 2 comma 0, and the y-intercept is 0, 10. And then for the increasing, so from negative infinity to infinity, we are increasing from left to right as we move across our graph. Our x values get larger, our y values are increasing the whole way. So this one doesn't have any decreasing. So then the end behavior for this is opposite of what we just wrote on the last one. The limit as x approaches negative infinity for the function is going to be going towards negative infinity, and the limit as x approaches infinity for the function goes towards positive infinity. So let's go ahead and analyze the graph of the polynomial function. We're going to use a graphing utility to help us. And so before we do that, we can still answer some of these questions from our knowledge of polynomials. So looking at the first one, be careful because you'll notice right here we have -2 and there's no x there. So if there's no x there, you don't say 0 equals -2. That's not true, right? So that's not a zero of our function. You're only solving the values that have the 0. So in this case, we have 0 equals x plus 2 and 0 equals x minus 2. And you can do the quantity 3 if you want. But again, that is not necessary because you're just going to get rid of that power of 3, take the cube root of both sides, and the cube root of 0 is just 0. So it's just easier to take what's inside and set it equal to 0. So here we get an x-intercept of -2, and here we have an x-intercept of 2. So on my graph, we have 2 and -2 for our x-intercept. So I'm going to go ahead and write that down here. So 2, 0, and -2, 0. Let's go ahead and find the y-intercept. So if we plug 0 into the function for x, we would get f of 0 equals -2 times 0 plus 2 and 0 minus 2 cubed. And so keep in mind that we know -2 cubed would be -8. So we have -2 times 2 times -8. So that's going to end up giving us 32 because we have 16 times -2, 32. So 0, 32. So on our graph, let's see if we count by maybe 10. So we'll do this as 10, 20, 30, 40. So 32 would be somewhere in here. I know that for this is a polynomial function, so the domain is going to be all real numbers. And not sure about the range because if we look at this and we count our multiplicities we have, this is a degree of 1, so 3, 4. So that means this is a degree of 4, which is even. And if we were to, again, think about multiplying this out, we have -2 times x to the first power times x cubed. So that would give us -2x to the 4th. So this is an even degree with a leading coefficient that is negative. So both ends of my graph are going to go down. So the limit as x approaches plus or minus infinity for this function approaches negative infinity. So both ends of the graph go down in this case. So for this, if we go ahead and put this in our graphing calculator, so let me get my calculator. So in my calculator, I'm going to plug this into my y equals, so -2 times x plus 2 to the first power and x minus 2. Now, before we were just graphing these without our graphing calculator, but let's go ahead and see if we can figure out, because we know that our graph has to have some kind of maximum over near on the other side. And we know that this is both ends of our graph going to be going down. So we know it's going to kind of go through like this. And this one's a cubic, so it's going to have a swiggle on it. So it's going to come down like this. And the other one's just to the first power. So it's going to come up somewhere. And on this side, you know, probably is coming down through here. So we probably have a maximum over here. So we're just going to use our calculator to figure out what that maximum is. So if I hit graph, I can see that I don't know what's happening with the maximum on my graph. I can see both ends of my graph are going down. I see my intercepts, but I don't have my, of course, y-intercept of my graph. So I need to change my window. My y-intercept is all the way at 32. So I'm going to go ahead and maybe put my y maximum at 50 and graph it to see if I can get that maximum on my graph. It looks like I'm still not quite high enough, so I'm going to go back to my window and the y maximum, and maybe I'm going to put it at 60 instead, and then hit graph. And so here's our graph. So we need to figure out what that maximum's at. So remember, to find the maximum, you can hit second trace, and maximum's number 4. And so the other day we were just sketching these without worrying about how high our graph's going. But if we have our graphing utility, we can, of course, use it. So left bound would be something to the left of the maximum. Right bound would be something to the right. Enter and enter for guess. So we get our maximums at -154. So I'm going to make a note here that the maximum is at -154. So that's 40. So 50 would be up here. So our graph goes something like that. And so for this one, our and the reason I wanted to find that is to help me find the increasing and decreasing interval. So our range then, of course, the highest we're going is up to 54. So -infinity to 54 bracket, because that's a maximum. So we are increasing from -infinity to the x value of the maximum, which is -1. And then -1 to infinity, our graph is decreasing. So let's go ahead and look at question number 4. So that one really, like I said, we could have kind of done it without using our graphing calculator. It's just then for the intervals of increasing, decreasing, we needed it. But if we look at question number 4, you know, trying to find factors of 0.5625 that add up to -2.5, it's going to be difficult. So we're going to use our graphing calculator to help us go ahead and graph this. So we have x to the 4th power minus 2.5 x squared plus 0.5625. And I'm going to go ahead and hit zoom 6 for standard window. Standard windows, remember, just graph from -10 to 10 and, for x and for y, because we don't always need such a large window. In our last window we had changed, so I put it back on our standard window. So it's hard to see what's going in here, but if I look at this, this is a degree 4, so this is even, and the leading coefficient is positive because it's already in standard form. So that means both ends of my graph are going to be going up, which is what I see right here. And I can see that I have 1, 2, 3, looks like 4 zeros. It's hard to tell what's going on right there in the middle. I don't know if it's bouncing on the x-axis or crossing through. So I'm going to change my window to zoom in a little bit. So maybe I'm going to do -5 for my x's and also for my y's. I'm just changing my window and then I'm going to hit graph so I can kind of see a little bit better, so I can actually see it is crossing through there. So let's go ahead and write our end behavior. So the limit as x approaches plus or minus infinity for our function f of x is going towards positive infinity. So then we know the domain of this is always going to be all real numbers followed polynomial function. And let's go ahead and find our x-intercepts. So to find the x-intercept, second trace, we're doing number 2, which is 0. We did this in the last unit. And we're going to scroll over to where our first 0 is and to hit something to the left, enter, and then something to the right of that 0, enter. And again, your 0 should be in between those two arrows. We talked about this in the last unit. Hit enter for guess. And we get -1.5. So one of our zeros is -1.5. 0, and then we're going to do this 3 more times. So second trace 0. So left bound would be again below the x-axis now, right bound would now be above, enter, and enter for guess. The next one is at -0.5 comma 0. So second trace 0, we're going to do this again and scroll over. So we have left bound, right bound would be below, enter, enter. So positive 0.5 comma 0. And then the last one, second trace 0. So below, enter. And then right bound would be above the x-axis for this side, enter, and enter for guess. And 1.5 comma 0. And then to do the y-intercept, you can plug 0 in for x. You're going to get 0.5625 or second trace value, and you could hit 0, enter that way and get 0.5625, or you could actually go to your table and see in your table. So let me change this so that's going by ones. So if I look at 0 in my table, you can see you get 0.5625 anyway. It works for you. So 0 comma 0.5625. So for this graph, then I'm going to also go ahead and find those minimum values. So I need that minimum right there. So second trace, we're doing number 3, which is the minimum. And we're going to scroll over and hit here, enter. Go to the other side, enter, and enter for the minimum. So we have a minimum at -1.1180 comma -1. So that's our first minimum. And then the second minimum, second trace, we're doing minimum again on the other side. And always round to 4 decimal places if you can. Enter. And then we go to the other side, enter, enter. So we get 1.1180 comma -1. So that's our other minimum value. So we can then go ahead and start to graph this. I'm going to go and zoom in so I can see a little bit better on my graph. So we have, maybe let's count by every other one. So we'll do this as 1, 2, 3, and this one is -1, -2, -3. And I'll do this as -1, -2, -3. All right, so we have our x-intercepts of -1.50 and -0.50. That's why I went by 0.5 from the graphs. It makes it a little bit easier to graph those values. and then our y-intercept is at 0.56, so about right in there. And we know then we can draw the rest of the graph. Oops, maybe, you know, I should plot my minimum, which is at negative 1.18, negative 1, so about right in there. And then the other one's at 1.1, so about right there. All right, so there's my graph. Now I can do the intervals for increasing and decreasing, and I can also write my range. My range is going from bracket -1 to infinity because that's a minimum value. It's the lowest of your graph. And so we're increasing from negative, or no, sorry, from, so I guess we would start with decreasing. So this first part of our graph right here is decreasing from negative infinity to that x value, which was the first one, negative 1.1180. And then for the next part, we can see from here to here, we're increasing. So we are increasing from negative 1.1180 to, you know what, and I didn't even write down the maximum right there, but the maximum was from our intercept, I think, but let's double check just to make sure. So second trace maximum, and we're just going to check because we're not 100% sure it's at the y-intercept, but just to check to see if it is. So yeah, so it is at the y-intercept, because remember, if you see negative 6.339 e to the negative 7, remember we said that just really means that you're taking that decimal place and moving it 7 places to the left. So you would have 0.0, 1, 2, 3, 4, 5, 6 zeros, and then 6, etc. So really that's just 0. So the maximum is at 0 and 0.5625. Okay, so it is. So we'll just say 0, and then the next portion we can see then from here to here is decreasing because your y values are going down. So we're decreasing from 0 to 1.1180, that other minimum value. And then for the last portion, of course, then your y values start to go up again. So then they're increasing from 1.1180 to infinity. And then I think we have, yep, everything for our graph. So that is how we would use our graphing calculator to help us analyze our function. And again, that's just review of the last unit because we also had talked about concavity. So we could also find the point of inflection on this graph, which remember is in between your max and your min values. So I could use that to add those values together and divide by 2. So just to show you for the first one, I have negative 1.1180 plus 0, of course, because that's the other maximum x coordinate is at 0. If you divide that by 2, we get negative 0.559. So if I went to my graph and hit second trace value, negative 0.559, I can see my point of inflection is at negative 0.559, negative 0.1210. So your curve bends upwards there, so concave up from negative infinity to that x coordinate, then it would be concave down and then concave up. So just a reminder for those point of inflections and concavity, because that's something else that we could, of course, ask again. All right, that is it for this lesson. I guess, you know, while we're here, might as well write down the point of inflections. So our first point of inflection was at negative 0.559 and negative 0.1211. So then our other point of inflection is the same thing, but it's positive because we're going from 0 to that 1.1180. So 0.559 would be positive. So if we were to go to our graph and hit second trace value 0.559, we get the same thing, negative 0.1211. So we would say concave up and concave down. So our graph is concave up from negative infinity to negative 0.559, and then from negative 0.559 to positive 0.559, we are concave down, because that's, again, this little portion of our graph right here. And then from 0.559 to infinity, we'd be concave up again. So again, this right here is concave down, or excuse me, concave up. This part right here is concave down. And then this portion right here is concave up. And that would be it for analyzing our graph.